All right, let's dive into something that sounds super futuristic, but is actually becoming more real every day.
Uh-huh.
Quantum assisted optimization, or QAO.
Yeah.
We've got a really interesting essay as our jumping off point here.
Okay.
QAO, Quantum Assisted Optimization for Complex Problem by Yorgo Schneepat.
All right.
And we're going to use this as our roadmap to figure out how quantum mechanics is going to totally change how you solve problems.
Definitely.
So think of this as like your cheat sheet to understanding all this complex stuff, but without getting bogged down in the technical details, you know?
Exactly. And you know how like a regular computer tries to solve a problem, like figuring out the fastest route on a map?
Yeah.
It basically goes through every single option one after the other.
Right, step by step.
Yeah, exactly. But QAO, it kind of flips that on its head.
Really?
It uses quantum mechanics to look at tons of possibilities all at the same time.
Whoa.
It's like that GPS example. Imagine it could see every possible route all at once, not just checking them one by one.
So it's not just a faster computer, it's like a completely different way of thinking about solving problems.
Yeah, exactly.
Okay, so let's unpack this seeing all possibilities at once idea a bit more.
Sure.
What is quantum-assisted optimization, really?
Well, at its core, it's about using quantum mechanics to make our optimization techniques way, way better.
Okay.
Like, when we have these super complicated problems and we need to find the absolute best solution out of millions or even billions of options.
Right, I'm finding the best way to schedule a bunch of flights or something.
Exactly. And we've been using classical optimization for ages, trying to get the most profit or using the least amount of resources. But sometimes those classical methods, they just hit a wall. They can get super slow, or they might not even find the absolute best answer, just a good enough one.
Oh, I see.
Especially when you're dealing with a massive amount of possible solutions.
So that's where quantum mechanics swoops in to save the day.
Exactly, and that's what makes QAO so exciting. It can potentially blow past those limitations.
So how did we even get here?
Well, it's a relatively new field.
Right.
It really started taking off in the early 2000s, thanks to some big breakthroughs in quantum annealing and the development of new algorithms.
Ah, so it's all about those quantum computers then.
Yeah, quantum computers are the key here.
Right. But are they really that different from the computers we use every day?
Oh, they're fundamentally different.
Okay.
I mean, think about it. Our regular computers, they use bits, which are either a 0 or a 1.
Like a light switch, on or off.
Exactly, but quantum computers use qubits.
Qubits?
And these qubits can be both 0 and 1 at the same time.
Whoa, wait, how is that even possible?
It's because of this mind-blowing concept called superposition.
Superposition, that sounds intense.
It is. It's like, imagine that light switch being both on and off at the same time.
Okay, my brain is starting to hurt.
The essay even has a mathematical way to describe it.
Oh no,
Don't worry, it's basically saying that a qubit can be in multiple states at once, until we measure it.
So it's like a coin spinning in the air. It's not heads or tails until it lands.
Perfect analogy.
So with superposition, a quantum computer can look at a ton of solutions simultaneously, something a regular computer just can't do.
Exactly. It's like having a massive team of processors all working on the problem at the same time.
That is amazing.
And there's another quantum trick up its sleeve, entanglement.
Okay, entanglement, hit me with it.
So imagine you have two particles, and they get linked together in a way that they're connected no matter how far apart they are.
So like twins separated at birth, but on a quantum level?
Sort of. It's like they have this invisible thread connecting them.
Okay.
If you measure something about one of the particles, you instantly know something about the other particle, even if they're miles apart.
That's wild.
Yeah, and for QAO, this means we can create these super complex relationships between the different parts of a solution.
So it's not just looking at possibilities. It's like weaving them together in this intricate dance.
That's a great way to put it.
All right, so we've got superposition, letting us see all these options, and entanglement, linking them together in crazy ways.
Right.
Is there anything else that makes this quantum optimization thing work?
There's one more key ingredient. Quantum interference.
Okay, interference, like noise-canceling headphones.
Not quite, but it does involve canceling things out.
Okay.
Think of waves, like waves in a pond.
Yeah, I can picture that.
When two waves meet, they can either make each other bigger or they can cancel each other out.
Right, so in QAO, we use interference to make the good solutions more likely and the bad solutions less likely.
Exactly. It's like the quantum computer is guiding itself towards the best answer.
I'm starting to see how this all fits together, but these quantum computers, are they even real? Like, can we actually build them?
Oh yeah, they're definitely real and they're being built right now,
Awesome.
but they're not like your laptop. They're super specialized machines.
So tell me more about these quantum computers.
So instead of bits, like in our normal computers, they use qubits, which we talked about earlier, the ones that can be both 0 and 1 at the same time.
Right, superposition and all that.
Exactly. And to control these qubits, we use quantum logic gates.
Gates, like logic gates in computer science.
Similar idea, but these work on quantum principles.
Okay, so are there different kinds of quantum computers?
Yeah, there are a few different types, but for solving QAO problems, there are two main ones we're focusing on.
Okay, tell me about them.
The first type is called gate-based quantum computers.
Gate-based.
And these are like the super flexible ones. You can program them to do all sorts of quantum algorithms.
Sound powerful.
They are, but there's a catch.
There's always a catch.
It's hard to build them with a lot of qubits and keep those qubits stable in what we call coherence.
Coherence, like keeping everything in sync.
Exactly. Think of it like a perfectly tuned orchestra. Any little disturbance and the music falls apart.
So losing coherence in a quantum computer means it stops working properly.
Yeah, basically the qubits lose their quantumness.
That makes sense.
Now, the second type of quantum computer that's useful for QAO is called adiabatic quantum computing.
Adiabatic, that's a mouthful.
It is, but it's a really interesting approach.
Okay, tell me more.
So these computers are specifically designed for solving optimization problems.
All right.
They work by starting in a simple quantum state and then slowly changing it to represent the problem you're trying to solve.
Kind of like starting with a simple puzzle and slowly morphing it into a complex one.
Yeah, exactly. And the idea is that the system will naturally settle into its lowest energy state, which corresponds to the solution.
So it's like the computer is finding the solution by following the path of least resistance.
In a way, yes.
So it seems like we're still figuring out the best way to build these quantum computers.
That's right, and there are some big challenges we still need to overcome.
Like what?
Well, as Mr. Schneppe points out in his essay, one big one is this thing called decoherence.
Decoherence. We talked about that a bit earlier.
Yeah, it's when the qubits lose their quantum properties because they get disrupted by their surroundings.
Right, like the orchestra getting out of tune.
Exactly, and that leads to errors in the computation.
So how do we fix that?
We're working on error correction techniques, which are like ways to keep the qubits in line.
Okay, so it's like having a conductor who keeps the orchestra playing in sync.
Yeah, that's a good way to think about it.
But it sounds like error correction is still a work in progress.
It is. It's one of the biggest challenges holding back quantum computing right now.
I see. So we have these quantum computers that use superposition, entanglement, and interference.
Yes.
But how do we actually tell them what problem we want them to solve?
That's where the algorithms come in.
The algorithms, right?
These algorithms are like sets of instructions that tell the quantum computer what to do.
So they're like the sheet music for our quantum orchestra.
Exactly. And Mr. Schneppot's essay highlights a couple of important ones.
Okay, which ones?
One is called the Quantum Approximate Optimization Algorithm, or QAOA for short.
QAOA.
Got it. And this is a really cool algorithm because it's a hybrid.
Hybrid, what does that mean?
It means it uses both quantum and classical computing.
So it's like a team effort.
Exactly. QAOA uses superposition and entanglement to explore a bunch of solutions, and then it uses classical computing to refine them.
So it's like the quantum computer comes up with the ideas, and the
Yeah.
classical computer helps to shape them into the best solution.
That's a great way to explain it.
And what's the other algorithm mentioned in the essay?
That one is called the Variational Quantum Eigensolver, or VQE.
VQE. Okay, what does that one do?
Well, it was originally designed for quantum chemistry to figure out the lowest energy states of molecules.
So finding the most stable configuration of a molecule.
Exactly, but we can actually use it for optimization problems too.
Really? How does that work?
We basically map the optimization problem onto a quantum system so that finding the lowest energy state gives us the solution.
So it's like turning our problem into a quantum puzzle and then letting the VQE solve it.
That's a good analogy.
And you mentioned Grover's algorithm earlier. Where does that fit in?
Yes. Grover's algorithm is a very powerful tool for searching through massive amounts of data.
Like finding a specific book in a giant library.
Exactly. And while it's not strictly an optimization algorithm like QAOA or VQE, it can be a really useful part of solving certain optimization problems.
So it's like having a super fast librarian who can find exactly what you need.
Yeah, that's a good way to think about it.
All right, so we've talked a lot about the theory of QAO, but are there any real-world examples of it being used right now?
Actually, yes, there are a few companies that are starting to use QAO to solve real problems.
Really? That's exciting.
It is, and Mr. Schneepat gives a couple of examples in his essay.
Like what?
One is a pharmaceutical company that's using QAO to speed up drug discovery.
Whoa, that's huge.
It is. They're using quantum computers to figure out how different drug molecules interact with biological targets.
So they can find new drugs faster.
Exactly, and that could have a major impact on healthcare.
Absolutely. What's the other example?
The other one is a logistics company that's using QAO to optimize their global supply chain.
So figuring out the best routes for their trucks and stuff?
Yeah, and by using QAO, they've been able to become more efficient and save money.
That's impressive.
It is, and these are just early examples. The possibilities are really endless.
Yeah, this all sounds incredibly promising, but what are the downsides?
Well, as with any new technology, there are definitely some challenges.
Okay, what are the main ones?
Well, first off, the hardware is incredibly complex and expensive.
Right, we talked about those delicate qubits.
Yeah, these quantum computers need to be kept at super cold temperatures and shielded from any kind of disturbance.
That doesn't sound cheap.
It's not. And then there's the issue of errors.
Decoherence again?
Yes, decoherence and other errors can really mess up the calculations, and while we're working on error correction, it's still a big hurdle.
So it sounds like we're still in the early stages of QAO, but the potential is huge.
Definitely, and there's so much research and development happening right now.
What are some of the main areas of focus?
Well, one big one is improving the algorithms, making them more efficient and able to handle more complex problems.
Right, like making our quantum sheet music even better.
Exactly. And another focus is on building better hardware, quantum computers with more qubits, longer coherence times, and better error correction.
So making our quantum orchestra bigger and more reliable.
Yeah, exactly.
And as this technology gets better, it's going to have a bigger and bigger impact, not just in science and industry, but in our everyday lives too.
Absolutely. Like Mr. Schneepat points out, we need to start thinking about the societal implications of QAO.
What do you mean?
Well, for one, quantum computers could potentially break our current encryption methods.
Oh, wow. That's a big deal.
It is, so we need to develop new ways to keep our data secure in a quantum world.
So post-quantum cryptography.
Exactly, and we also need to make sure that everyone has access to the benefits of this technology.
Right, so it's not just about building bigger and faster quantum computers. It's about making sure they're used for good.
Exactly, and that includes educating people about quantum mechanics and its potential impact.
So wrapping this all up, QAO is a super promising field that could revolutionize how we solve complex problems.
Absolutely.
It uses the crazy power of quantum mechanics to explore tons of solutions at once, but there are still some big challenges to overcome.
For sure, but the future is bright, and as we continue to improve the technology, who knows what amazing things we'll be able to accomplish.
Exactly, and it makes you wonder, how will this ability to solve super complex problems change how we think about efficiency and problem solving, not just in industry, but in everyday life too?
It's a question we should all be thinking about.
Absolutely. Well, this has been a fascinating dive into the world of quantum-assisted optimization. A huge thank you to Jorgo Schneepat and his essay, QAO, Quantum-Assisted Optimization for a Complex Problem, for guiding our discussion.
Definitely a great read.
Until next time, keep exploring, keep learning, and keep questioning.
Sounds good.
And we'll see you on the next deep dive.
See you then.